So this is the first chapter. Like I said, we're actually going to start talking about the atom and parts of the atom in particular. Okay, and even though the history may be interesting for some, I will not test you over the history portion. Okay, I give a little bit of the background on the history just because of the fact that it helps explain what the parts of the atom are and how they came to be. But I want to ask you, okay, what year did John Dalton propose the atomic theory that it's not the scope of this class? So that's not nothing that's going to be really useful for you later on. So you don't have to worry about those. But I still would expect you to know atomic theory, okay, that everything's composed of atoms, since, okay, and know what the parts of the atoms are. But I'm not going to ask you to say what year did they come up with the plum pudding model or anything like that. Okay. This is nothing new in the sense that everything is composed of atoms. In atoms, what we'll see is the smallest, once again, the smallest thing that you can break it down into with it keeping its identity for that element. Okay. And this is just to give you an idea that everything is composed of atoms. And so they're telling you, you got the air and you've got the water, they got triethylamine, which I wouldn't ask you what triethylamine is. That's an organic chemistry question, except that's the reason why it smells fishy. A lot of times amines will smell, and sometimes the medicines will be in amine. Anything that's in amine, sometimes they kind of smell, have that fishy, or almost like a dead kind of smell. Okay. Now, one thing is, just to get a scope of the size, I do like this, just to try to help you visualize what it is atoms are really small. You cannot see an atom with the naked eye. And so if you get an idea of how small an atom is every atom with a little pebble, or the size of the actual pebble itself, then it would reach the top of Mount Everest, the highest point in the world. And so, yes, if they are just the tiniest piece of grain or whatever it is that you see is actually composed of, billions of atoms. Okay, and so that's why they are very, 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 very small. Now there are, just to do a review, like I said, most of this is just a review. Atoms are composed of matter. It's the smallest identifiable unit of the element, as I mentioned before. I won't ask you about the numbers and the fact that there's 91 that occur in nature and 20 or so that are synthetic, because as I think they tell you here, yeah, it is kind of controversial because some of the ones that they thought were only synthetic may occur in trace elements in nature, and so I wouldn't ask you that, or ask you, I will not have you memorize, okay, what is number, 87 on the periodic table? It's francium. No, but if I give you a periodic table, I'd expect you to be able to find number 87 francium on the periodic table. So, but that's pretty straightforward. Okay. So as I mentioned before, John Dalton, the 1808, he's the one that actually proposed what's called the atomic theory. So this is the important part. Don't worry about the years. And this is held true throughout all time. So atomic theory, there are three parts. One is every element is composed of atoms. Okay? Now he said that they're indestructible. Now we can bombard them to break them apart to subatomic particles, but they're no longer that element. Okay, so that's one little caveat in there. Number two was that all atoms of the element have the same mass and other properties that distinguish them, it makes them different. That there's a little asterisk by. We're going to find out that that's not necessarily true. It's only partially true. Okay. That was before the idea of isotopes, and I'll explain what an isotope is later on. It is true that all atoms of a given element have the same number of protons. That's the important thing. The number of protons is what's going to distinguish, one atom of one element being that element versus something else. And then, once again, atoms combine in simple whole number ratios to form a compound. That's why we have two hydrogens that go together with one oxygen to make water. 4 hydrogens go with 1 carbon to make methane gas. And that's true. You can't have a half of an oxygen. Or a half of a hydrogen. It doesn't work that way. this is just cool. I think it's cool. This is where, you know, they're microscopic, but IBM has taken a scanning electron microscope, and xenon, which is a it's a decent sized, large atom, but we still can't see with our naked eye. And they use that microscope to push the xenon atoms to spell out IBM. It's a little side note, atoms are roughly spherical. However, due to the machine itself, it made it look like a cone head, each atom. But so you can see atoms with a scanning electron microscope, or scanning tunnel microscope here. Okay, there's a lot to this, but it's actually a fairly simple idea. This is the plum pudding model that I was talking about. It's by J.J. Thomson. He is the person who came out and discovered the electron. Okay, so we have an atom. This is the first of the subatomic particles. The atom itself has negatively charged electrons. And I won't ask you how he discovered it or anything like that. However, he knew that it made sense that you couldn't have something negatively charged without having something positively charged to counterbalance it, or otherwise it would explode. So he's like, there's got to be something positive around. So he had this idea, you know, he's British, so he's eating his plum pudding, and he had this idea that, you know, the electrons are like the raisins or whatever that's in the plum pudding, and the rest of it's positively charged. It's kind of like this milieu, this mess. Okay, that's wrong. Okay, but I'll tell you that part. There are electrons. Electrons is correct, but it does not look like plum pudding. Next came along Rutherford. I want to explain this. This is what it looked like, but I'm going to explain. He's gold. It was an expensive experiment even back then. Right. And gold, one of the properties is you can make gold foil, like make it really, 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 really thin. And so if you irradiate or you excite lead, it is also called an alpha particle. It's part of nuclear chemistry. It's actually a clean atom, but it's an alpha particle. And he shot that alpha particle through the gold foil, and he had film put around it. Okay, and he noticed the idea, according to plum pudding. Here I'm going to show the next. I think it's the next slide. It does a much better job. And we're just going to look at this part. I didn't make most of these, and so they're very text heavy, which is good for like reviewing on something, but make for boring presentations. So this is the idea with, let's say, yeah, it's a good one. So if those alpha particles, if it's a plum pudding, when you shoot it, the electrons are believed to be really, 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 really tiny. And so the odds of the alpha particle actually hitting an electron and being deflected are negligible. So therefore, the alpha particle should just go right on through and hit that film that was up there. Remember, it kind of looked like this. There's the film or the detector. The gold foil was here. And so we had the alpha particle would just go right on through, essentially, and hit the back side. However, what he noticed was some of them did go through, but then some of them actually got reflected at different angles and hit along the sides. So therefore, it couldn't be plum pudding. Instead, what he ended up discovering, was the proton, and in particular what's called the nucleus. And the vast majority of the atom is made up of space, and the nucleus is relatively small. And that space, we're going to call it, it's the electron cloud that surrounds the nucleus. But the electrons are ridiculously tiny. They're like 1/2000th. It's technically, I think it's 1/1836 or something like that. I would never ask you to remember those, but they're just really, really tiny. But the nucleus itself is relatively dense. That's where virtually all of the mass of the atom is in this tiny, relatively small nucleus. But since it's dense, as those alpha particles were being, shot through, some of them hit the nucleus and bounced back. Some of them barely grazed it and bounced askew. And then, like I said, some of them didn't even hit the nucleus at all and went straight on through. But this proved the idea that there is a nucleus, and the nucleus contains the positively charges. Okay, and that's what this next slide is showing. Like I said, this is called the nuclear model. In reality, the nucleus itself is smaller than what's depicted here. It's just so that way you can see it. And once again, it's approximately 1 electron in size is approximately, equal to 1 over 2,000 of a proton. I mean, it is ridiculously tiny. However, they have opposite charges. The electron has they give it a -1 charge, and a proton has a +1 charge. So as long as you have 1-to-1 ratio, it's neutral. But most of the atom is empty space in the nuclear model. Okay. Are there any questions so far? So we have the atom. The atom itself is primarily empty space, but it does have this dense nucleus in the middle. The nucleus itself contains the protons, which are positively charged. The empty space, that electron cloud, contains the electrons, which are negatively charged, but they're really tiny, even smaller than the nucleus, and they have a much, 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 much smaller mass. Later on, they also discovered there's something called a neutron. A neutron is about the same size as a proton, has the same mass, approximately, but it has it's neutral, it has no charge. That's what's depicted there in the darker color. Thank you. So this is just to give you some idea of what I've said so far. The nucleus itself makes up more than 99.9% of the mass. However, it just has a very tiny portion of the actual space. It's very dense. The electrons are distributed through what many people call the electron cloud. However, there's it depends on it, but relatively few, but they have very, very tiny mass. It's essentially zero. And they themselves don't take up a lot of space either. Then this gives you an idea that, if a single grain of sand was a solid atomic nucleus, it would have a mass of 5 million kilograms, which is blows your mind. A single grain, if it was only all nuclei. That's the plural of nucleus is nuclei. One of my pet peeves, and President Bush used to do this all the time, and it drove me nuts, is this word. This is one of my pet peeves. Whoops. Pronouncing this word. It's nuclear, not nuclear. So there's just 2 U's in there. Just one. New and new. Clear. C-O-P-A-R. Nuclear. Okay, so the nuclear mass is made up of protons and neutrons.
Wait, how did you say it?
Nuclear. Yeah, maybe my wife says it that way sometimes.
I'm pretty sure I say nuclear.
Nuclear energy. No, it's nuclear. No, everyone's going to think, how do I say it? Nuclear. Because if the NU wasn't there, it's just a clear, like a clear day. But yes. See, now that you're going to... Okay. All right, this is just another idea, just a way for you to help visualize what's going on. If the proton was the mass of a baseball, with a regular baseball, then the electron would weigh the amount of a single grain of rice. Okay. And so that's why if you have something like, you'll find out helium, which has 2 protons and 2 electrons, it'd be like having 2 baseballs in your hand and adding these 2 little individual grains of rice. The grains of rice really don't change the mass of whatever's in your hand. So that's why whenever they figure out mass, they don't actually include, typically, like if I asked you to calculate the mass of something, you wouldn't include the electrons. The electrons have, there's no way to get 2,000 electrons, and we could go up to, 111 on that periodic table. 118 in theory so far. So there's no way for them to even equate to a single proton. All right. This you actually already know this without thinking about it. So this is just the whole idea of attraction and repulsion. Similar signs, same signs will repulse each other. Opposite signs attract. So the electrons and an electron and a proton would be attracted to each other, whereas 2 protons are going to be repelled by each other, or 2 electrons are going to be repelled by each other. So there's this interplay between that helps hold all of the atoms together. And that's actually also where the neutron comes into play, because if you have this little dense area of just protons, they would want to explode, but neutrons is like a buffer and neutral. You don't have to have a neutron. One type of hydrogen doesn't have a neutron, but it only has 1 proton. So, okay. And to get the charge overall, you just add the number of protons and add the number of electrons, and whatever that number is overall, it's the charge of the atom or the ion. They haven't learned that yet. Okay, so if it's neutral, we're going to have the same number. All right, so to put all this into summation, this is like, to really drive it home, this is the important part to know is this right here, okay? So we have 3 subatomic particles that there are actually more. You can break them apart even more. You may have heard of some of these like quarks and things like that. We're not going to go there. Okay, so you can have a proton that's positively charged, so it's got a +1 charge, an electron which has a -1 charge, and a neutron which is neutral, a 0 charge. Their relative masses, this is where this would get scary. Remember, the kilogram was the SI unit for mass, but it's just ridiculously tiny, right? Because a proton is 1.67 times 10 to the -27. Right, so that's just, when we talk about atoms, we don't like to use kilograms. What they do is they use what's called the atomic mass unit, which essentially what it is a proton that's equal to 1 AMU. The neutron is also equal to 1 AMU, and an electron would be equal to 1 over, I think it's like 1,836, or something like that. Some, 0.00055, it's still almost 0. So that's 27, 8, 9, 30, 31. So it's 10 to the -31 for an electron in kilograms. So it's the protons and neutrons have about the same mass. They're essentially 1 to 1. The electrons are negligible. Okay. You want everything, if at all possible, to have equal numbers and be happy. When things go awry, bad things can happen. That's actually why lightning occurs. Because during a thunderstorm, the electrical potential changes. You have more negative charges in the sky, more positive charges on the ground. And to equalize that, the lightning technically runs from the ground to the sky, will run up and creates a lightning bolt. Now, we're going to find out there are ways for an atom. Yeah?
Do you know why Florida is like the lightning bolt capital? Does that have something to do with like the ground being more positively charged?
No, it has to do a lot with the bodies of water around it.
Okay.
So yes, and it's only the lightning capital of, and it's this part of Florida. Central Florida is lightning capital of North America. There is another part of the world that's in Africa that actually has even more lightning than we do. But yes, it is. It also has the highest per capita number of people that get struck by lightning, by the way. But we have bodies of water, you know, on three sides: the Gulf, the Atlantic, and then we have the Straits of Florida. But what would be the Caribbean Sea down at the bottom. And so the weather here is completely different than anywhere else in the United States. It's difficult for the jet stream, which is what dictates the other 49, well, not Hawaii, but it dictates for 48 of the states, the weather. It's really hard for it to come all the way down to Florida. Very rarely, only in the wintertime do we see it sag as far as Miami, typically. So because of that, our weather is dictated by the water. So we have the winds, and the reason why, how many of you guys are actually from Florida, from this area of Florida? Actually, so quite a few of you are. Then the idea is, and so you haven't really been here too much, those who aren't from Florida, in the summertime. But you know, during the rainy seasons, we have our afternoon storms. Typically, the reason why is that we have two huge bodies of water on each side, and the winds come off the Gulf, the winds come off the Atlantic, and they hit. And since they have different temperatures and they have to come from different directions, they collide, and wherever they collide is where you get that whole line of thunderstorms. Usually they don't last very long. Whichever one is the more powerful one will cause it to move one way or the other. So that's why if you always look in Florida, a lot of times during the summer, during rainy season, they have a really long line of thunderstorms. They're called the sea breezes when they collide. Okay. All right, so how do atoms differ from one another? Why isn't everything looking like hydrogen? Hydrogen is the most simple. Hydrogen has one electron and one proton. That's it. Okay. But as you can see, and it's in the uppermost levels, number one, on the periodic table. So as I mentioned before, it's the number of protons that say what an atom really is, what element it is. It's not the number of electrons. Because we're going to find out that it's possible for an atom to lose an electron, become positively charged, or to gain an electron, become negatively charged. For whatever reason, and I don't know historically, they give the number of protons the letter Z. And so if you hear something said like a Z, that's telling you the number of protons. Whereas mass is the letter M, which makes sense. So Z for helium is 2, and for aluminum is 13, carbon is 6, oxygen is 8. The higher the number Z, the heavier the element will be, the more it will weigh, have a larger mass. Okay. And we group this on the periodic table. So depending upon, I think our periodic table is actually very similar to that one. It doesn't have the name of the elements on it. But some periodic tables may have a bigger number on the top and a lower number on the bottom. So this is the periodic table. All elements will have a 1, 2, or 3 letter code. Whenever I was in school, they only had 1 and 2 letters, but now some of them have 3. For those that are still not officially named. Okay. You always capitalize the first letter. It's very important. That's how you know when you're running a chemical formula. When one element ends, the next element begins is based off the capital letter. So I will deduct points if you don't capitalize or use lowercase correctly, because it means completely different things. Okay, so they're showing beryllium right here. The smaller number of the two, there's always at least 2 numbers. One of them has to be a whole number, because you can only have whole numbers of protons. That tells you the number, that's Z. That tells you, it's called the atomic number. So, like I said, sometimes they may put it up here, or they may switch the 2 places. It doesn't really matter. Okay, but the whole number is Z. Remember, that's the number of, number of protons. The larger number, here, the 9.01, it's called technically it's the average atomic mass. That's the measure of the average mass of all the beryllium in the universe. Okay. What they do is they just take a really large sample of it and divide, and they assume that comes out. And that has to do with the number of, that's based off of neutrons and protons, and we'll discuss that further later on. Probably not today, it probably won't be until later this week. Okay, and then this 2-letter code, for most of them's 1 or 2-letter code, is the chemical symbol. Ours on the wall doesn't have the name, but this one's beryllium. They may also give you other, depending upon, which I didn't look to see what one's in your book, they may also give you other information. Some of them may give you what's called oxidation states, which is how easy what ones will want to gain electrons or lose electrons, and they can give you lots of things, whether it's radioactive, what state of matter it's in. Most of them, well, we'll find out this later on. Many of them, maybe I'll let you know if it's a solid versus a liquid. There are only 2 that are naturally liquids, that's bromine and mercury. or if it's a gas naturally, or stuff like that. But at the very least, it will give you Z, the atomic number, the atomic mass, and the chemical symbol. Okay. And we're going to talk about how they're grouped together, because it does matter. Oh, that's really cool. It makes my words get really tiny, too. Good to know. All right. Some of the chemical symbols are based off of English, so they'll make sense. Beryllium, Be, that makes sense. There are some that make no sense whatever. For historical reasons, maybe they're based off of German or Latin. For example, I wouldn't ask you like what language. I know that tungsten is based off of German. It's Wolfram in German, so it's the letter W. Sodium is natrium, which is Latin, so that's why it's Na. But so some of them you used to seeing like Na and K. K is potassium. Some of them just have to memorize. Once again, I'm not going to ask you to memorize the periodic table. There's some that I would expect you to you should pick up on, like carbon, oxygen, nitrogen, things like that. If it was something like silver, I would give it to you at this point in time. Whereas maybe for an upper level class, I would ask you to memorize some more of the elements. Okay. This just lets you know that there are other ones that have, whether they're named after countries, or they're named after mythology, or they're named after what have you. Or people, like Rutherfordium, which is named after Rutherford, came up with the idea of the nucleus. Einsteinium. There is an actual board that meets and decides the name. Okay, so you can lobby to try to get names made, or get this has been named after you or your place. Some of them were named after scientists. Marie Curie, of course, won the Nobel Prize. Actually, she won 2 Nobel Prizes. Famous woman scientist, worked with radiation, radioactivity. And a little side note, my alma mater is in the University of Missouri, and the Curies came and worked there for briefly. And so they have some of their work there, and of course back then they didn't know, because she died a relatively young woman from cancer. They didn't have any idea what radiation would do to your body. And so they're just working on with radiation and all this kind of stuff, and their lab notebooks and stuff that the University of Missouri has is still radioactive. And so it's like you have to sign something or wear special materials and stuff to go in there and actually hold their books and things like that. They're kept under lock and key. But yes, just a little side historical note. Bromine is named because it smells really bad, but don't ever sniff bromine. Not only does it smell bad, but it's highly toxic. So don't do it. He'll die. It's like chlorine gas. They're related.
Okay.
So typically, bromine and chlorine are both highly reactive. Can be highly reactive. They can form free radicals relatively easily and react to. It's called halogenation. Halogenation is various materials in the body. Okay. All right. So then come Dmitri Mendeleev, and by the way, Mendeleev is named after him. But what he did is he started noticing, there's certain things like chlorine and bromine that they have similar properties. So what happens is trying to put them together in a table to where we line them up based off of their properties. Like, do we see something, like, is there an order? Like, do you see something over and over and over repeating again? And so he starts with the things, at least at that time, what was the lowest in mass, and he started writing them out and figured out, okay, this one is similar to this one, and this one's similar to this one, and notice that, there are properties that seem to repeat regularly based off of the mass. Okay, and they call that, these properties recur periodically, so that's why it's called a periodic table. Yeah. And so, even though good old Dmitri needed a good haircut and shave. All right, so this is what his work looked at. Like I said, they didn't have nearly as many elements that they had isolated and named and known at that time. But lo and behold, I have color perception problems. I can't tell you what the colors are. But you start lining them up, and lithium and sodium and potassium, this color, they all have similar properties, whereas really magnesium and calcium are very similar. And you have fluorine, chlorine, and bromine, which you got there that are similar. And so that's what they noticed, that this happened. So that's why we started to arrange them in rows and in columns, and use the periodic table. They do have, some of them do have special names. Like this very first column, they're called the alkali metals. I wouldn't ask you at this point in time to know, versus alkali earth metals. With the exception of maybe this one. Does anyone know what this last column is called? The very last, the one that's really, column 18 on there. They're called the noble gases. They're also called the inert gases. Because, not nerd, inert, I-N-E-R-T. Because for the longest time, they thought that they had no reactivity whatsoever. They were perfectly happy. Then they were content. And that is true, particularly with ones that are very light. But those that are really heavy, actually, you can do chemistry with them. They didn't know that at the time. So we'll talk a little bit more about that later this week as well, I'm sure. But, okay. So I'm actually going to skip over this word. So, what does this tell? I can't really tell colors apart at all up there. So, my drawing may be a little off. Please forgive me on that one. But, in general, they also noticed that certain elements with certain properties are in certain areas of the periodic table. And so there's this stair step right here that runs through, at least through to this point. Like I said, some of the 117, 118, those are theoretical, so they may not have been isolated. They may not be so on a name yet. So right here, at least at the time of this PowerPoint, 117 IUPAC is the board that means. So anything, with the exception of the elements that touch two sides of that stair step, anything to the right. So what is this color up here? Whatever that color is, those are nonmetals. Okay, explain what that is later on. Anything, once again, with the exception of aluminum and, oh, they actually included polonium in this one. Well, aluminum, at least. So, and hydrogen. Hydrogen is a special case, but anything like this, and what's called the lanthanides and actinides, all of those are metals. So most elements, if you take guess, it's going to be a metal. So they have metallic properties versus non-metallic properties. Those that are right along that stair step are called metalloids. They have certain properties that are like metals and certain properties that are like non-metals. It's almost like a buffer But yeah, lanthanides and actinides are both metals as well. You guys don't, I'm pretty sure, it's not part of the ILO, so I wouldn't ask you. But there is a reason why it looks like this. Okay. Because technically, it would be another dimension of the periodic table coming out like this, because all of these have to fit in with little spaces. And there's a reason why, it's really difficult to explain. It's like the whole chapter on itself. So right now you just have to take it. Those are metals. Yeah?
Does the periodic table ever change? Like, within a certain amount of time? So like
I mean, really not since in the last, what is that, a couple hundred years, 150, 200 years, that they don't change the order. That doesn't change. Because if you notice, it goes in whole numbers based off of the number of protons. But what has changed with time are, as they discover new ones, like through down here in particular, then this gets filled in. And so that's why if you look in some of the older textbooks, these won't be there, or they'll say like UUP, which stood for like ununpentium, I think, and then there's ununhexium and ununheptium, where they were theoretical. Ununoctium. So they didn't make sense. But now they start putting them in. So as they get discovered, and then as IUPAC, and it's going to be not only discovered once, but it's going to be repeated multiple times, and then IUPAC gets nominations for names, and then they vote, and that becomes a name, and then it gets added to the periodic table. So they add, but they don't take away necessarily. Okay.